right, so these are the two problems from class, and once I got home, I realized what, what I was doing. I was confusing myself. Okay, so for this first question, um, again, it's going to, the limit as coming from the right is going to go to 0. Um, and the conceptual thing you're looking at is that the area of the triangle is bigger than the area of the circle. You could put some numbers in there, I guess, and then calculate it. Um, but certainly as theta becomes smaller, so this side's coming in, this side's coming in, um, we draw that and we'll get something like this. So when the triangle's like that, then the circle's just going to be like that. Um, the thing is these are functions of theta, and actually the way I did it, I, I didn't work with theta. I realized that the base of the isosceles triangle was also the diameter of the circle, which would make half of it the radius. So I called this length here, we'll just call it B. That's what I did. So the area of the circle becomes, since it's only half of a circle, it's half of a circle's area. The radius is 1/2 B. It's only from here to here, and I called the whole thing B. And then we square that. So, oh, I know what I forgot though. Pi r squared. So there's a pi in here, um, which may throw my system off a little bit. But the area of the triangle is 1/2. So we see that's going to cancel out. Base times height, so base is B. And the height could get calculated. You could split it into two triangles. Again, really to do this, you could look at the using theta. But then when you multiply all this out, the 1/2s cancel. We square this and we get 1/4 B squared pi over BH. Now that 1/4, the way fractions work, this will push the 4 down to the bottom. This B cancels with one of these, and so we're left with B theta, no, sorry, not B theta, B pi over 4H. Um, and again, looking at this, because it's an isosceles triangle, H is going to be much larger than B, especially as that um, as theta gets close to 0. You could have many different styles and probably find an example that doesn't work when it's large. But as theta gets smaller and smaller, the relationship between the base and the sides and the heights is going to be smaller and smaller, as we can see. So I just look, okay, the bottom is going to be larger as this goes. So what's going to happen is the top will go to 0 first. And the bottom actually doesn't quite, the area will go to 0, but but H doesn't go to 0 completely until it completely collapses. So this will have a number other than 0. Um, and so the limit will go to 0. Um, Again, if that's not convincing enough for you, set these equations up in terms of theta itself, and that can be done. Someone after class shared that with me, shared a way of going about that. Okay, so for this one, this is a different setup. Let me see if I can get all this one I did use it in terms of theta. Uh, and noticing that the circle itself, that this radius and this radius uh, are going to form the same. And what's going to happen here as theta becomes smaller is we still have the r the same, which is an isosceles triangle. But what's going to happen is the amount of the arc is going to be smaller, and also the base is going to be smaller. So I've got a little bit of uh, help here. Looking up arc length formula, that's going to be pi times r. And then how do we find the length of d itself using some trigonometry? Looking up the area of an isosceles triangle, the area is 1/2 s squared sine theta. Um, Now, that in itself, so and again, in our example, rs is, we're calling it r because it's also the radius of the circle, right? Um, the other thing is that the perimeter is going to be, in our case, the perimeter of this triangle is going to be 2r plus d. Um, and so what we can do is, or what I did is, let's see if I can, okay, so that's perimeter. So I was looking at that because what I want to do is I want to get it in relation to what is d. Um, so what I did is that the area of the triangle is going to be 1/2 r squared sine theta. But the area is also, if I just do it, if I were to calculate the height, um, it's going to be 1/2 the base times the height. The base in this case is d, and the height is some value. Now what I'm going to do is as theta becomes smaller and smaller, I'm taking advantage that this radius, the height and the radius basically become the same. So I'm going to, and again, this is it's not a exact proof, but it is an intuitive thing that certainly as theta gets smaller and smaller, the height is going to go to r. So I'm going to basically make a substitution as theta gets really small. We're at r, and so you can see we can do some divide both sides by, or multiply both sides by 2, that goes away. Divide by r, and what we get is that d equals r sine theta. And then we take that along, we take the ratio, because that's what we're looking at, s, the arc length over d. So that gives us that we have r theta for the arc length, and then we have r sine theta. So the r's cancel. So we end up with theta over sine theta. When you graph this, and I'd encourage you to do that, I did it with Desmos, what you see is basically, let's switch colors here. You'll see a graph that comes down like this. There is a hole here at 0, so we are definitely using limits, but the limit, as you see, as you get closer here, it's getting towards 1. So the answer here is going to be 1. They basically get to 0 relatively at the same time. I guess what that means, there's some other parts to the graph, but this is the one we're interested in, is as we're getting close to 0, we've got this. And again, I did that with taking a little liberties on what the height of the triangle is going to be. But yes, as we get very, very close, it's going to be so close to r, that part doesn't really factor in. Okay, so that's the way I took a look at it. and I hope you find that beneficial. But again, with limits, what we're looking at is sort of um, intuitive feel for things as we get close to zero.